The classroom video for WJC A-Level Maths Unit 3 Pure M2.3.7 D3, the product rule and integration by parts. So if we're asked to integrate the product of two functions, we need to reverse our trusty product rule, and you met this in M2.3.6b2, and your two functions are typically in x, but they don't have to be. They could be in theta or anything else. And so what we get is the differential of uv, where u and v are functions in x, is given by v du by dx plus u dv by dx. Now clearly I've chosen that order. You will frequently see u dv by dx plus v du by dx. Doesn't make any difference. The operations are multiplication and addition, both of which are commutative. In other words, the order doesn't make a difference. I personally always put the v1 first because it does make a difference with the quotient rule. Not relevant in this case, but it's just why I do it. If we now integrate each term with respect to x, and there are three terms in this function. So there's my first one on the left hand side of the equal sign, and then my two terms separated by the positive on the right hand. I'll get the integral of d by dx uv with respect to x is equal to the integral of v du by dx with respect to x plus the integral of u dv by dx with respect to x. Now we know, ought to know, but we should think about it, that integration and differentiation are reverse functions. So therefore, if I differentiate something and then integrate the result, I'll get what I started off with, uv. So this gives me that uv is equal to the integral of v du by dx with respect to x plus the integral of u dv by dx with respect to x. No real problem. And I can rearrange that. Now, however I choose to rearrange this, it doesn't make any difference. Basically, this comes down to the integral of u dv by dx with respect to x is equal to uv minus the integral of v du by dx with respect to x. And of course, I could have v du by dx with respect to x on the left-hand side. Hence, I'd get uv minus integral of u dv by dx with respect to x. It doesn't make any difference. Okay, so, but this tends to be the format that it's seen in most commonly. In order to carry out this function, you've got to decide, because you've got to compare your integral u dv by dx with respect to x with the thing that you're trying to integrate. And if you know what u is, then in order to get the du by dx, you need to differentiate that. If you choose what dv by dx is, in order to get what v is, you've got to integrate that one. So you've got to differentiate one bit and integrate the other, which seems a bit strange that you're going to use a mixture of differentiation and integration, but it relates together, and it's because it's reversing this product rule here. So the technique is called integrating by parts, because you partially integrate each bit, and you need to remember the pattern of the rule. You won't see it in your formula booklet, so you need to learn this particular beast. And so I've bolded it up for you, that the integral of u dv by dx with respect to x is equal to uv minus the integral of v du by dx with respect to x. So if I do an example, and in this particular case I want to deal with the integral of x e to the x with respect to x, clearly it's the product of two functions. One of them's the x and the other one's the e to the x. Now in this particular case, being bright, intelligent human beings such as you are, you could easily differentiate the x term or indeed integrate it. You could also differentiate the e to the x term or indeed integrate it. So you've got to make a choice. Now it makes sense to actually differentiate the linear function, the x function, not the exponential function, because if you differentiate your linear function, it just becomes a constant, and therefore it makes life that much easier. So I would perhaps suggest that you should usually differentiate the linear function or the straight algebraic function and integrate the other function. So in this particular case, I'm going to choose to do, as I've suggested, that u equals x, hence my differential of that, du by dx, is going to be equal to 1. And because I chose to let the u equal x, it follows that my other function from my equation, the dv by dx, must be equal to e to the x. Hence v is the integral of e to the x, and the integral of e to the x is e to the x. So as I said, it's easy to do either with these two functions, but it will work quite happily. So my integral of x e to the x dx equals uv, where u is equal to x and v is equal to e to the x, minus the integral of v du by dx, which is e to the x times 1. Now e to the x times 1 is nice and easy to do because it's just e to the x. So therefore, going through this, I'll get x e to the x minus e to the x plus a constant because there are no limits. And I probably didn't really need to put the constant in there, but I like to emphasize that fact there. And then really I would expect, seeing as this is A-level maths, I would anticipate that you would take out a common factor, and you can see the exponential function e to the x is a common factor in this particular case. So therefore my final answer, which I'd be delighted to give an examiner, would be e to the x bracket x minus 1 plus a constant. And it's relatively easy to do. Now if you'd chosen to choose them the other way around, in other words, you'd let u equal e to the x, then your du by dx would be equal to the e to the x. But in which case your dv by dx would be equal to x, and your v would become the integral of x, which is x squared over 2, and it's making it more complicated. And you've got something that's even tackier to integrate. So just it would keep on, it would be getting worse and worse and worse to try and integrate it. So in general, as I said, differentiate the algebraic function, the strict algebraic function, and integrate the other function.